Good morning, good afternoon, and good evening. I'm your host, Aya Takasen, and I am here with our presenters. So, co-presenter Simon Bates will facilitate the Q&A sessions, and we have two experts with us today, Dr. Genesis Infante and Dr. Akhilesh Tripathi as speakers. And Genesis is joining us from CTherm today. Now, thank you for joining us for our webinar series, Enhancing Pharma Processes with X-ray, Thermal, and Raman Analysis Tools. In this webinar series, we will discuss various practical analytical techniques and their applications to enhance pharmaceutical research and quality control. The episodes are organized by the different stages of a research and production. And in this second episode, we will cover analytical techniques related to preclinical and preclinical development, and preformulation. But before we start, a few housekeeping items. This is going to be an interactive session, and I'll be posting relevant links in the chat window, and we'll be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. And please submit those questions via the Q&A button at the bottom of your screen. We will not be monitoring the raised hand function. And we will try to answer as many questions as possible during the webinar, and we'll be responding to any unanswered questions by directly contacting you after the session is complete. If for whatever reason you have a difficulty viewing the webinar live, please note it is being recorded, and we will be sending you a link to the recording beginning tomorrow. Now, with that said, I'm gonna give the floor to Simon.
Greetings and welcome everybody. Before we get started on this webinar, I'd just like to introduce you and set the stage to our webinar series that follows the drug development pipeline all the way from early discovery through development through to the final manufactured drug product. And today we find ourselves in preclinical development and formulation, and we have two speakers to enlighten us today. The first of those will be Genesis, who will talk about thermal methods and products, and they'll be followed by Akhilesh, who will speak to us about X-ray powder diffraction. And just to reiterate what Aya says, please ask questions in the Q&A button at the bottom. Don't be shy. Please ask questions. Having said that, I'll pass you across to Genesis.
All right, everybody. Hello. Thank you for the introduction. So I'll be covering the presentation about using thermal analysis techniques to accelerate preclinical development of pharmaceutical products. My goal today is that I hope that everyone that participates will gain some insights and lessons about the applications of TG-DTA and DSC techniques for preclinical development, and insights about the mass loss, dehydration, glass transitions, polymorphisms, how thermal analysis optimizes formulations, and hopefully your clinical or study stability. But before I'd like to, before I start, I'd like to ask everybody of a question.
Okay, so Genesis has a question for the audience. I'm gonna launch the polling question. So the question is, which thermal analysis techniques have you used in your field of work? So you have multiple choices, TG-DSC, or TG-DTA and a TG-DSC combined, or something else. You can choose the other, or you might say, I don't use thermal analysis. And if you choose the other, we're curious what you have used, and if you can put what technique you used in the chat, that would be great. The answers are coming in fast, and we're almost, I'm gonna wait for a few more seconds. Okay, now I'm gonna close the poll in 3, 2, 1. Okay, let's take a look at the results. So 68% TG, 71% of you chose DSC, and 32% for TG-DTA DSC combined, 10% other, and 60% are new to thermal analysis.
All right.
Yeah,
So go ahead, Simon.
yes, of course.
All right. So that really tells me that this would be a relatively easy intro for me. And for those that doesn't use this technique, I hope, and if you're not familiar with it, I hope you will learn something in general. So, the first question would be, what does thermal analysis tells us? For this quick intro, I'll be covering two general concepts. First one is the thermogravimetric analysis, or TGA. And this technique typically, it's pretty straightforward. It covers or monitors the mass change across, as temperature increases. And basically, there's three possibilities that could happen. One is that nothing happens, so the mass doesn't change as temperature increases, or you'll have a mass loss. Well, you have a negative percentage right there as temperature increases, or a mass increase as temperature increases. So either of these cases tells you that something happened to the sample and something changed with your mass, and you can combine that with the other analysis techniques, such as the heat flow analysis techniques that we'll be covering today. It can really give you a full story of how your materials behave under different temperature. So the other techniques that we'll be quickly going over would be different heat flow analysis techniques, specifically differential thermal analysis, or DTA, differential scanning calorimetry, or DSC. So for both of these techniques, essentially what we'll cover is we'll be monitoring changes in terms of energy or temperature with your material. So y-axis typically shows a heat flow value and a directionality. So in this case, down means that the energy is being absorbed. And again, our x-axis will be the same, increase in temperature. And the basic typical results should look like something like this, where either you have a baseline shift. So this typically is associated with a transition of sorts, a glass transition, phase transitions, or a exothermic reaction, such as that you'll have an increase in heat flow, or the opposite, endothermic, where you have an absorption of energy. So before I go forward, I'd like to just kind of reiterate the biggest differentiation between the DTA and a DSC. So for the DTA, as the temperature increases, what we monitor in this technique is the change in temperature between the sample and the reference. So if something reacts that releases or absorbs energy within the sample, that difference in temperature is recorded within the DTA technique. The DSC technique it goes a little bit more into that. It follows a similar concept as temperature increases. However, the difference is that what we monitor here is the change in heat flow between a sample and the reference. So again, if you have if you're a release of energy, you'll see an exothermic increase in the heat flow, and if you have absorbed energy, you'll see that decrease in energy. And again, the biggest difference is that in DSC, because we're monitoring heat flow, we can actually characterize the energy associated with those reactions. So the area under those curve is basically energy as expressed in joules per gram. So I'll be covering two techniques for this part of the webinar. One of them is the combined technique of TG-DTA or TG-DSC, and the one that is just standalone. So, this slide should be, will be showcasing the biggest difference between the two and where you should be applying with this in terms of your application. So, melting, if you're looking at the melting, for example, both of these techniques are very well suited for it. Crystallization, glass transition, phase transition, in a technical sense, both of these techniques can be applied. However, DSC has a slight edge since you can actually gain a little bit more information from that particular reaction. Dehydration, both can really cover those. However, something like decomposition, evaporation, sublimation, and water vapor absorption, reactions that tend to have an associated mass loss or mass gain, the DSC is really not as suited because, like, you can't really tell unless you have that mass loss, mass gain data associated with it. So first, I'll be covering the advantages of the TGA-DTA technique for preclinical development. First example would be something along the line of pre-screening. So effectively, something like if you have a sample, but you don't know how that sample will behave in a thermal environment, it is highly recommended to use the TGA before you proceed with a DSC, for example. So as a case here, we have caffeine. So this is the TG data on top and the DTA data on the bottom. First, you should notice that there is a phase transition at about 160 degrees C and a endothermic event that is associated as melting at about 235 degrees C and decomposition. So I know that this is a decomposition based on the TG data. So as you can see right here, even starting at the phase transition, you can see that there is a mass loss occurring, and that mass loss rapidly increases as we approach the melting temperature. And at this point, at about 280 degrees C, you'll see that there is that 20% or 30% decrease from the beginning. So this tells me two things. One is that I should probably do a measurement next time with a DSC with a pan close. So, if I proceed with DSC measurements, you'll have a DSC that is a sealed pan. That avoids that preemptive mass loss that might be caused by evaporation. And two is that now that I have that baseline figured out, you'll see that it is, you can characterize the melting, but we shouldn't test it beyond a certain temperature because decomposition starts occurring. So that's one of the examples where STA or the TG-DTA can really offer a advantage over the DSC. Another one is processing, basically the effect of how mechanochemical processes can really change how pharmaceuticals or similar products behave in general. Another one we'll be covering the water content for this one. So first, with mechanochemical effect, you'll see is the sulfamic acid right here. The original version would be non-treated sulfamic acid tested. You'll see the TG right here in red and DTA at the bottom in red again. So you can see that there is a melt and then recrystallization. And then once we pulverized it, and then what happens? So what ended up happening is that mass loss occurred in an earlier temperature, and that melting and crystallization occurred again in earlier. So it shifted and it changed the behavior overall. This one covers the thermal behavior of carbamazepine dihydrate using TG-DTA. You'll see again the TG, this is the derivative of TG to show that there is two distinct process here. You can see that there is two distinct different mass loss events. And you can associate that with the TG-DTA, you have two endothermic events at 62 and 68. And this is the loss of the dihydrate portion. So beyond 100 degrees C, you'll see that it is effectively anhydrous. And then at some point when it starts melting at a 185, you'll see that there is also associated mass loss with it. So, based on this, you can get really some insights on how or what temperature you should be treating this molecules overall. The next part I will be covering would be the thermal behavior under the relative humidity, so controlling the amount of water content in the air. And we can achieve that by having this humidity controller attached to the TG-DTA from Rigaku. And typically there are two modes that you can do a study with here. First, you'll have a temperature increase, but a steady control in the vapor partial pressure. Or you'll have a steady temperature and a varying vapor partial pressure as a factor to change. One case study right here is the water absorption and dehydration of alpha cyclodextrin. And as the blue is the humidity, the red is the temperature, and the green is the TG data. So the first part right here, you can see that there is a pre-drying treatment. So temperature went up all the way to about 180 degrees C, and you can see that there is that drying 10% mass loss due to drying. And as temperature goes down, some of that mass is retained at about 1.6%. And this is probably associated with like leftover water vapor inside the chamber that get reabsorbed back to the cyclodextrin. And then the next steps is the changing of the relative humidity. So at this point, you see the drastic increase of 90%, and you can see that that absorption is occurring, retaining that 10.8% mass at some point. And then, you cycle through it, dry and high humidity, dry. You can see that it goes through this mass loss, mass gain cycle overall. And you can see that the absorption is actually slightly exothermic. You can see that there's a slight bump during that increase in during that absorption step. So at this point, I'd like to take a breather and have take some questions from everyone.
Yep, that would be great. We have one question posted online. What is the value of pre-screening using the TG-DTA, and what are the risks of directly using the DSC without knowing this thermal behavior?
Yeah, that's a very good question. So, the first thing that I showed earlier is the pre-screening capabilities or the advantage of the TG-DTA. It really comes down to the construction, the design of the furnace itself. So the TG-DTA is designed to account for any decomposition occurring because you're monitoring the mass change and mass gain in there. So you'd expect that within the test profile, you'll have a decomposition occurring. So there is an outgoing flow occurring all the time. So any decomposition byproducts that might be produced that could be harmful to the instrument are off-gas relatively quick. On the DSC, it's not as well designed to that. Typically, DSCs are contained within a chamber. And it's effectively what it boils down to is that you want to mitigate risk with your instruments overall.
Okay, that's great. Thank you, Genesis. We do have a couple of other questions, but I think in the interest of time, let's continue, and then we'll see at the end if we have time to address these questions.
All right. So now, I guess it's my turn to ask everybody a question.
Okay, so let me start the second question. Okay, so the question is, do you find thermal analysis useful for your work? Your choices are yes, no, or you can also say, I don't know. Okay, so answers are coming in fast. Almost, okay, over 70% of you answered. I'm going to give you a few more seconds. Okay, so I'm going to close the poll in 3, 2, 1, and share the results. 97% of people said yes. This is very encouraging.
All right. Yes, that's awesome. All right. So, very quickly, I'm going to go cover cases, application notes that involves the DSC, differential scanning calorimetry. So in pharmaceuticals, typically, crystallinity is very important as a concept. So in this case, shown in the screen is the DSC signal from terphenadine, and there is a amorphous signal portion, which is basically the glass transition associated with the molecule, and a crystalline signals that is associated with melt, right? So, a glass transition is effectively a signal that is very common for our amorphous characteristics, while a sharp melting is typically associated with crystallinity. So, from this on is that I'll be covering examples that shows how we can tackle crystallinity in general of pharmaceuticals and the effect and how polymorphs can comes into play with this, effectively comparing amorphous versus crystalline, and of course the effects of impurities. So very quickly, with DSC as a technique, I've mentioned earlier that you can quantify the energy flow associated with that particular event. So for an example, for a melt, we can characterize how much energy is associated with that reaction. So for calculating, the crystallinity, we can use this energy by having a sample that we know 100% to be crystalline. And then, if you have your unknown sample, we can have that energy compared directly to it. And it's, you just do a ratio from there. The pro for this is that it's relatively easy because, it's a direct math to it. The problem becomes when polymorphism is involved. So you can't be sure if that within that signal, there's other signals that are associated with it or polymorph with it. So the other portion would be if you have polymorphism and you have, amorphous signals from the signal, like a glass transition, you can use that also to calculate crystallinity. So in this case, you'll have something that is fully amorphous, so it's like a 0% crystalline sample. The con is that it is difficult to sometimes determine crystallinity based on this process or method because we're really looking at the shift, right? So case in point, we're looking at acetaminophen here. We have three cases. One is that this black line right here, this is a fully crystalline acetaminophen, so 100% crystalline. And the green is 0% crystalline, so fully amorphous acetaminophen. And you have this unknown test sample in blue. So, you'll take the difference between the baseline, between the 100% crystalline and the amorphous, or the test sample, sorry, and then the difference between amorphous and the baseline, and you'll see the ratio right there, and you subtract that from 1, and you get a ratio, which is 0.57. You multiply that by 100%. You basically get the calculation of about 57% based on this data. So this tells you that this is partially crystallized during whatever process it was done with, and you can go on from there. Another point here is the effect of impurities to the melting point of a crystalline substance, right? So a pure substance, something like this with no amorphous signal shown right here, you'll have a sharp melting temperature, well-defined and sharp. And then, in a case where there's a green signal right here, there is an introduced some impurity contaminated into it. And you can see that the melting changed by some broadening right there and a slight shift on the melting point overall. Quantification of that impurity, if you don't know what that impurity or how much impurity is in there, we can go with using the Van Hoff freezing point depression formula. T0 is essentially the temperature of melt of a pure substance. The R is it's a constant or a gas constant, and the HF is a molar heat of the melt of the pure substance. And what you're looking for here is the X2, which is essentially the amount of impurities in a molar fraction. And the T is the temperature where that impure version of it melted. And in this case right here, this is showing different phase transition of polymorph. You can see that in the alpha, there's that alpha to gamma transition at 114. And then at a beta to gamma at 119, and with a gamma, there's really no one of that transition overall. Here is an example of, I think, unique capability shown by Rigaku in general is the sample observation, where you can see right here as, this is again carbamazepine being exposed to increasing temperature. You saw that there's a quick melt and then recrystallization, and then another melting event at about 193 degrees C, I believe. And, so this capability, the sample observation attachment basically, really drives the point that you can have a full story of how your materials behave in general, and you can associate that thermal event with a visualization on top of that, right? We can infer a lot of information based on what we know in general, but it's really hard to really be sure about it until we have another layer of data included to it. So just going back to that DSC analysis, basically we'll start with that 0 degrees C at room temperature. You see that white powder. At 170, there's really no change. But then at 177, you see that very quick melt, and basically a melting of the metastable phase, and a quick recrystallization. And then from there on, you'll have a increasing in melt. So from 178 to 185, there's really no change. And then you see that quick real melting at 192, and then transparency at 193. And at the end of this webinar, I'll be covering dynamic DSC, often called as temperature modulated, basically covering some reversible and irreversible process, and of course, specific heat capacity. So for all those that doesn't know, dynamic DSC or modulated DSC is effectively a modified DSC where the temperature increase is not linear. It is in a sine wave type cycle. And there's an amplitude and a period involved with it. So it goes up and down in a certain frequency. We can, and with this method, we can start separating reversible versus irreversible process. So for a reversible component of this equation, for the total heat flow, you'll have the CP, and then something like the glass transitions and the melting, and the non-reversibles for the rest of their type of reaction, right? So biggest value for dynamic DSC, so this is the dynamic DSC associated with terphenadine, with this condition right here. The biggest value for dynamic DSC is that, out of all this data, you can start separating things like the phase transition. So something like a glass transition that typically are in a small, small peaks. There tend to be small peaks and small energies compared to something that are very exothermic or very endothermic. They tend to be covered and overlapped by these other broad signals. So the dynamic DSC offers this capability to be able to separate that. And you can see here that the non-reversibles are separated in this red signal, and then on this pink signal, you'll see that they're reversible. And you can see that you can't really tell from the original data that there is a glass transition at about 60 degrees C, right? So having that capability, you can get this insight from it. And on top of that, you can actually get the specific heat capacity on top of all this DSC signal. So, the value of modulated DSC is that you can do all this one test with all this data associated with it. So that's the end for my presentation, and I hope that everyone, got some valuable information about how we can apply these techniques, pre-screening with your processes, crystallinity, polymorphs, and of course, visualization of your thermal events and modulated DSC. And with that, I open the floor for questions.
Yeah, thanks again, Genesis. We're really short of time, so I only pick one question. If you have a quick answer. This is from Nico, and they ask, is the sample observation attachment included in the TG-DSC instrument?
Yes, actually. The TG-DTA, both TG-DTA and DSC from Rigaku has a module for sample observation.
Okay, thanks, Genesis. We sort of run out of time, so we'll pass the baton. Thank you.
Okay, thank you, Genesis. And if you have more questions for him, you can connect with him on LinkedIn and continue the discussion. I'm gonna put his LinkedIn profile address or URL in the chat. Okay. Now let's move on to the next part. So Akilash, you ready?
Yep. Going to share my screen. Is my screen visible to you all?
The editing mode, not the presentation mode yet.
It's on the full mode now? Yes?
Yes, yes it is.
Okay, thank you. Thank you, Genesis, for a wonderful lecture. And thank you, Aya and Simon, for introducing me earlier. And I welcome all. So let's move to the second topic of the day. Unlocking drug potential, the role of X-ray powder diffraction in preformulation. So in this series, you will learn three parts. What is X-ray diffraction? We will cover some special cases such as XRD, DSC, preferred orientation, small amount of sample, liquid, gels, creams, air sensitive, and highly potent sample. And then we will look into some applications. So before we delve deeper, let's, like the previous speaker, let's have a polling question so that we have some feedback.
Okay, so let me start Akilesh's polling question. So he wanted to ask the audience on which process do you use XRD in? So we have multiple choices. A, discovery. B, preformulation or formulation. C, preclinical or clinical. And D, regulatory review. E, quality control. And F, other. And G, you might say you don't use X or D. Okay, so questions are coming in fast. I'm going to give you a few more seconds to think because there are so many choices. I guess if you're in one of those processes, you know which one to choose. Okay, I think most of you answered the questions. I'm going to end the poll and let's share the results. It's pretty evenly distributed, but 63% said pre-formulation formulation. And discovery, preclinical, clinical on about 30 to 38%. And regulatory review, 19%, quality control, 50%. And actually 20% of you said other. If you can let us know which process you use X or DN in the chat, that would be great.
Thank you. That was good. And that brings us to my conclusion that we can cover all these topics. So let's begin with what is X-ray diffraction, the first topic. Before that, as Simon showed, and the polling also showed, the importance of powder diffraction in pharmaceutical development from discovery to development, pre-formulation to formulation to manufacturing. Where does XRD play roles? And as most of you already answered, it plays role almost in all these parts for your work. So let's go delve deeper into that. What is powder X-ray diffraction in its very simplicity? So you have a source of X-ray through an instrument, and you have a sample, such as a pharmaceutical sample. It would diffract X-ray, and a detector will detect it based on Bragg's law, and likely you would have one of those patterns. One crystalline pattern where the peaks are very well defined, and it can match very well with a database or with your own database. You may have a amorphous material, such as a hump like this. Usually they are pretty similar. Or you can have a mixture of crystalline and amorphous, which is like you have a crystalline phase, and for example, an excipient, which is usually a binder or a filter, could be your amorphous main. So powder X-ray diffraction pattern in general can be divided into three categories. If we delve deeper, a crystalline phase will have a very lattice kind of formation. That is, you have a crystal structure. Polymorphs may have different crystal structure, but similar chemical formula, but your pattern is very well defined. An amorphous material with a hump, as we saw earlier, and your materials is not well defined. There is no lattice, i.e. a repetition in the crystal form. So it's a haphazard arrangement of atoms, and hence an amorphous pattern. Or you can have a mesophase, which is a state between crystalline and amorphous, exhibiting properties of both. It has some degree of molecular order like crystals, but also retains the fluidity of amorphous material. It's quite common to see this sort of disorder. So one, we can tell using a powder diffraction pattern easily, is my material crystalline, amorphous, or a mixed mesophase. If it is a crystalline, how do we proceed? For example, this is an example of a crystal form or API carbamazepine. You have a clear-cut pattern. You could have your own database. So you can collect a pattern of a pure API, for example, save it as your database and match it. That way you know when you have made a polymorph or when you have made the correct API. So you have a clear match. So first, we get the idea, what is my crystal polymorph? Next, what about quantitating it? Suppose you've made both the forms, both polymorphs. One of them is perhaps your API, another is your other form, and you want to know how much it is mixed. So one way we can do it is using a quite accurate approach called calibration curve. As you can see with this arrow, suppose you have a polymorph, talbutamide, and its amount, which is proportional to its integrated intensity, is here. So you can translate it into a y-axis intensity, and upon translating it to an x-axis, you can tell its concentration. And this calibration curve has been previously prepared with a pure form, for example. So you know that if you keep adding, you can create a calibration curve with different amounts. And wherever this lies further, the amount can be easily told by a calibration curve. So hence you can do a quantitative analysis. So what do we learn? How much is my form 2 present? How about percent crystallinity? Like I said, in a lot of cases, you have API that you mix it with a binder filter, or which we called as excipient material. So in order to tell how much is my excipient, because that eventually controls the behavior of a drug, you can do percent crystallinity analysis. So usually in XRD, it's quite straightforward. The integrated area under crystalline peak is compared with the integrated area as shown here under two amorphous peak. The ratio of them can tell you what is your percent crystallinity. To give you an example, we'll delve deeper into this. Limit of quantitation can go quite steep. Amorphous quantification by direct derivation, one of our DD methods, using a type C2 function is shown on indomethacin. And here you can see the crystalline form is continuously reduced from 3% to 0.5%. 3% here in the black diffraction pattern with an amorphous sum, and 0.5% in this blue, and almost 0% in the red. Very little crystalline material here. The prepared phases were 3 to 1.5 to up to 0.5. And using this limit of quantitation DD method, we can relate it to 0.7. That's pretty close to what was prepared. So that's how low you can go. This is one example. Relative intensity ratio. Let's look into more quantitative method, RIR method. We call them generally simply integrated intensity methods. So in this case, we are showing, for example, you can take the highest peaks of the two phases mixed into each other. They have been ratioed, or there is a general RIR factor or a number associated with a common denominator, such as a corundum. So let's say if you collect your pattern and mix it with corundum, you generate an RIR number based on the highest pattern of your phase compared with the highest pattern of corundum. And this RIR number will then act as a scale factor for you to compare the ratio of any two phases mixed into it, any two, any three, any number of phases. So these are simple semi-quantitative methods that can be employed in X-ray diffraction technique. Using the RIR technique, you can tell the amount of each of the phases. How about more detailed situation? We can employ methods such as refill, poly, or direct derivation methods. These are profile fitting method by least square method. Let me explain a little bit how they work. So if we could tell, for example, in refill method, it's based on the structure factor, because structure factor is directly proportional to intensity. In fact, square of structure factor is intensity. So Dr. Refill found out that if we could tell the phases of a particular compound which it is made up of, it can generate a model pattern, i.e. a simulated or a calculated pattern. It will lay over the actual diffraction pattern that you collect on your diffractometer. And when the match is good, as indicated by several residue factor, and you can also observe that in this case, blue is right on top of red, you have a very low residue here. Once that is done, i.e. the model is very close to the calculated data, you have all the information. Not only just the amount of phases, but the unit cell and ESDs in them. So those all can be performed. So this is Rietveld analysis, very strong tool for the quantitative and unit cell work also. How about the one we saw earlier, the calibration curve method? If you could identify a pure phase, you can always create and store calibration curve. For example, this is a calibration curve based on the different amounts of anatase, 0, 1, 2, 0, 1, 3, and 5%. And Against this calibration curve, you can always run your unknown with wherever the intensity of that peak lies in here. For example, you can extend that calibration even curve downwards to know that amount. So these are known as spiking methods. The only caveat is you need a pure phase to generate a calibration curve. And you can use standard materials also to check them, the variation in intensity. Also, just to mention, calibration curve can be created for multiple phases at a time, not just one phase. So next, changing the topic to what would be the instrument. So I could generally divide Pharma XRD instrument into two types, floor models and desktop models. So let's first see a floor model, such as this Rigaku's Smart Lab. You could perform a number of analyses. Let's point them out: screening or cluster analysis. Each one of them, by the way, could be scaled up. So screening or cluster analysis, where you can screen a lot of pre-formulated drugs or something in solution format, where it is extending to in the function of temperature. You can study precipitation. Ex situ studies you could do to check crystallinity check. You could do in situ studies of two types, study the crystallization using XRD-DSC, which we will delve into. You could also study dissolving API or adding excipients. How is that changing over a function of time or temperature? You could study polymorph, phase ID, or low quant. So in general, if I could put a statement to it, floor models are suitable for research and development. How about benchtop metals, such as the one shown here is Rigaku's MiniFlex, 6th generation? You could essentially use it for every part of powder diffraction pattern. They do come with regulation compliance, CFR Part 11, electronic record and electronic signature. In short, we call it ERES. That is, they are compliant with. In situ, you can employ two temperature changes, two temperature stages. We have 0 to 150, room temperature to 150, and a negative to 500 to do simplified in situ work. Or you could study multiple samples, which I mean polymorph, excipient APIs using them. So if I were to put a statement for benchtop instrument, benchtop models are suitable for all powder applications. At this point, I would like to see if we have a question based on what we have covered so far.
Yeah, thanks, Akhilesh. Just a quick note, I noticed that someone has raised their hand. We're not checking the raised hands, so please ask a question in Q&A. We have a lot of questions. If I pick one from Nico, it's a long question, so bear with me. Typically, a standard curve is built with 100% of each phase, crystalline and amorphous. But when amorphous material crystallizes, it usually does not go to 100% crystalline directly and shows up as a broad peak rather than a sharp peak. How do you account for this transition or transitional phase in quantitating percent crystallinity?
So, yeah, that's a long one. There are a bunch of approaches to doing, I understand your need. So there is something we do called comprehensive analysis. Again, this would be based on integrated area under the amorphous peak. It will also always be in the ratio of amount of amorphous. So if your amorphous, for example, is 90%, the integrated area under it would be higher. There is another approach we also use in REITville known as partial or known crystalline structure, or in short, the acronym for that is PONCS. In PONCS, what we do is we will assign either by ourselves or just using a DD method, we will assign a curve which mimics your amorphous material, and then we can assign it to a very highly asymmetric space group, for example, P1 or P bar 1. This kind of space group can encompass all the other space groups. So you can essentially solve any structure in P1 or P bar 1, and then you assign a unit cell. Once those are matching well, you can save it as a crystallographic information file or a CIF file. Now, this CIF file can be combined with the other structures, and you can get the exact quantitative amount, whether it is increasing or decreasing as you described in your experiment.
Yep, thank you, Akhilesh.
If we have no more questions, shall I proceed? Simon?
We have lots of questions, but I think it's good if you proceed, yes.
Thank you very much. So let's see some special cases, because we all come across these special cases, and with my experience in this field, then we need to know how can we handle them. So we will briefly go over some of them and let us know if you have question. One is XRD-DSC, preferred orientation, small amount of sample, liquid, gel, cream, i.e. these kind of samples, air sensitive or highly potent sample. Genesis did a wonderful job to make my job easier. He described the DSC very well, differential scanning calorimetry. What I'm trying to do is tell now the synergy between the two, how both XRD and DSC combine together to give you a lot more information and clarify in certain situation. So just briefly, we saw that in Genesis lecture, that how a downward trend endothermic reaction versus an upward trend exothermic reaction could be classified into, for example, an exothermic situation could be happening where we have a phase change going on, beta or gamma phase of a polymorph. Or in a downward trend, we see order to disorder or crystalline to amorphous changes going on. Or further along the path, you can also see if the phase melted and a new phase beta, gamma, or alpha emerged. So how could these information relate with XRD to give you more information? So here is Rigaku's Smart Lab equipment, which also comes with attached DSC, i.e. both of them can be combined into one platform. So you have a reference sample and you have your own sample, and typical ranges or amount of sample are given here, 3 to 10 milligram, room temperature to 350, or you could also have under special situation, minus 40 to 350, you could use the atmosphere such as static air, inert gas, or humid air. Let's see one results. The things would be pretty clear with that. So for example, you are taking your sample from a room or low temperature to 140 degree, and then you are going back to a certain temperature, let's say 30 degrees centigrade. So in this, you see in the DSC curve, as we were showing in the first picture, is going through a number of changes, what we talked about, endothermic and exothermic changes. With XRD, what you are also getting is, for example, you start with form 2, red here, and it retains itself to this very point where we see a phase transition. And we do see that this red pattern changed into something different, a blue pattern. You can see a new peaks here in the blue that was not in the red. So you can identify which phase got formed at this point. And then you see a big change in the DSC curve where the melting is happened. And sure enough, after melting, we do not have a crystalline form. We have an amorphous form going on until the temperature 78 degrees centigrade, where you have recrystallization or any crystallization phenomena to a different phase. And there you go. The green pattern shows a new phase being formed, and then you can identify it. So DSC along with XRD makes a powerful tool to not only see the changes in DSC, but to relate to them, whether it's an amorphous and crystalline phase or whether it's an alpha, beta, or gamma, which phases are being formed. By the way, this study is for tall butamide form 2 under dry nitrogen. That is where this study was performed. So XRD-DSC can continuously monitor the changes in crystal structure during heating and cooling. Let's turn into a different aspect of diffraction, where it is also important, texture effects, or in also short known as, the texture effects are also known as preferred orientation. In nature, we also see this. In nature, for example, I have just shown in nature, it is even present. Halloysite and kaolinite are two different minerals, clay minerals. One is formed in the fiber format. If you go to a museum, you'll see them in the fiber format always. And kaolinite, which is more like a plate-like format. What happens in X-ray diffraction, if you do not take care of this, the phase which is more visible to X-ray upon diffraction, for example, if you put them in reflection mode, you will see only this phase or this phase, and you will get preferred orientation. This green peak is raised because, for example, let's say this is OOL peak, 004 peak. So 004 peak is enhanced because X-ray is seeing it most of the time. It doesn't see these edges unless you take this into account and use an appropriate geometry or method to circumvent this. So for example, here in transmission geometry, we are more likely to see these edges also besides the flat plate, and we will get more closer to theoretical pattern, which is in orange, The purple pattern looks more closer to the theoretical pattern. And as we manufacture drug, for example, we have seen this, I'll just simply say a simple aspirin, there is a lot of preferred orientation. So preferred orientation can affect your percent crystallinity and your amount of phase, because yes, peak positions are retained, but intensities are not right upon preferred orientation, and intensities are related to the amount of the phase. That's why it is important to take care. There are a number of ways where preferred orientation can be minimized. One of them could be the techniques, textbook techniques, where well-known back-loading or side-loading, that were the earliest techniques. Nowadays, people use some other methods, such as you can make a slurry and let the slurry slowly crystallize so that the crystals have all possible orientation on a zero background flushed holder. So that is easily possible because you have these zero background flush holders. You can also take a brush, drop a powder onto the slurry or onto a grease which doesn't have its own X-ray signature. This will let this small crystal drop on it with every possible orientation. Remember, our goal is to see the edges, not only just the flat sides or only the fiber. So that makes it more random. You could do spinning. One way of spinning is one-dimensional. It's not highly effective, but the best spinning would be using a transmission geometry, capillary spinning. Miniflex, I have shown a picture here, which has a capillary stage where you can spin the sample. It's like more three-dimensional spinning. And again, you can see the edges, not just seeing the flat part of the crystal, which is only possible in one-dimensional spinning. Next, I have two special cases. One is, what if we have a very small amount of sample? It used to be a challenge, but there are two ways I want to address this. We have zero background. This is present universally. Zero background holders are special cut of silicon in a direction which doesn't cause any diffraction pattern, such as a HKL direction of 510. We have a 5 milligram sample powder and a 1 milligram or less sample holding powder, this kind of sample holders. This is the rectangular version of them. You can see, if you can see the powder, almost if you can see the powder, you can have a pattern. In this case, it's just 0.2 milligram of corundum, and you can match it with corundum. This is 0.1 milligram of theophylline anhydride. Almost you can see it, but you can match it here again. Even this is mixed with lactose hydrates, the purple one, that's also visible. So you could check with that even that this is a mixture of two, and you could go this low. The second aspect is more related to the new optics and the detector types, which allow you to go pretty low in concentration in certain cases. In this case, again, the case of theophylline monohydrate and anhydride, this amount of sample present in as low amount as 0.1 of the total mass percent can be detected. You can see there's a bulge in the peak here. This part is zoomed out, and you can see 1% is so well visible, even 0.1% can be visible. So it is with the advent of, like I said, more advanced optics options, and especially with the detector technology, you could go very low percentage of mass detection. Airtight sample holder. Sometimes we are in a situation that the sample is reactive either to the humidity or just simply with the air. It will decompose over a period of time, i.e. it is a sort of transient sample. If we want to run such sample, we need some special sample holder, airtight sample holders. We should employ them. Here is a case in point is iron chloride, just to show it over 20 minutes of period, it almost amorphizes, as you can see. So start with an iron chloride, it's beginning to amorphize, and in 20 minutes, it's gone. Total amorphous pattern. However, in an airtight sample holder, such as this shown here, even after 120 minutes or 2 hours, the powder diffraction pattern of the same sample is well retained. And you can see the powder diffraction pattern is more crystalline and well defined because this sample, even in the process of putting it in the diffractometer, it is beginning to amorphize. And this sample is prepared in a glove box. How about liquid sample? Liquid samples are slightly challenging at times, and not all liquids are crystalline also, but there are situations such as this is sunscreen lotion and liquid sample, and it is filled in a liquid sample holder, this sunscreen lotion, and we can obtain a diffraction pattern using such sample holders, wherein we are showing in sunscreen lotion the phases, zincite, rutile, and tall. All these three phases are clearly present and are shown. Let's now move to the topic 3, the applications. We'll cover 3 topics here: crystal forms, high throughput screening, direct derivation, in short DD, and cluster analysis. Investigation of crystal forms. So when we are working with pharmaceutical drugs, at times our goal is to make a new drug. And in the new drug, one of the challenges is to find the crystal structure, or at least to perform the indexing. So indexing can be performed much easier when the system is correct and when we can identify the peaks very well. So a K-alpha-1 system, such as one shown here, Rigaku's SmartLab Johansson monochromator 1, which is easily switchable with K-alpha, can just produce K-alpha-1 peaks, and your indexing can be well performed. Together with specialized indexing format, rational indexing, what we call, this can be done very well. In case details about rational indexing is required, do let us know. We have a Dick-Wall program that picks up among the best possible 10 crystal systems, and knowing the volume percentage of the asymmetric unit, this can be well performed using a rational indexing form. High throughput screening. So we are in a situation trying to develop a new drug. We have lots of polymorphic forms. We have lost a lot of initial formulations that we want to analyze quickly. One way to do is a AutoZ focused this special plate, high throughput screening plate that Rigaku has in the Smart Lab, wherein you can even define the coordinates and XY of the formulation that you want to look into. For example, you want to go to this formulation, you will get the XY coordinate of that, which you can attain by putting by clicking at that point. That actually coordinate is generated, and you can get the data using the XY motion in this stage of all these possible formulations. So now you have a lot of data. So you need to sort this polymorphs. So in this case, you have collected a lot of data. So you can use the cluster analysis and use a threshold bar. You can see we employed a threshold bar to classify these clusters based on this threshold bar. And what you generate is what we call as dendrogram, or a tree diagram. What it does is it organizes the data into some sort of clusters. In the dendrogram, the data located nearby have high degree of similarity. Conversely, the data which are far from each other have a very low degree of similarity. So you are grouping the data in terms of similarity, and that can go into a relevant program such as powder diffraction and analyze automatically, and a report is generated. So you can use this sort of sorting polymorphs by approaching cluster analysis, and you can make a report. So cluster analysis to extract reference pattern, endomethacin case. So for example, here's a lot of data in this overall formulation for endomethacin. From crystalline to amorphous, you can, using the cluster analysis, what you can do in a process-wise is you can extract components. So for example, in this case, we have extracted 4 components, 2 amorphous component and 2 crystalline. The crystalline components are different based on the preferred orientation. Now, any mixture of this, which I'll show in the next slide, any mixture of this crystalline and amorphous form, once we have extracted, we do not need any database. It's an absolute quantitative method. Employing the DD method and cluster analysis, you can find the ratio of any of these two forms present in any amount. That's the idea of component analysis that you can perform. So group data according to the similarities in similarities in the XRD pattern, and this is something called as PCA analysis. Okay. At this point, are there any questions? Actually, that's the end.
Yeah, we do have questions, Akhilesh, but we've got 0 time. I'm sorry. But thank you again. It was very interesting.
Thank you.
Okay, so the questions we couldn't get to today, Akhilesh will be reaching out to you directly to address your questions. Okay, so as I said earlier, recording of the webinar will be available tomorrow, and an email will go out to all registrants with a link to the recording page. Links to the resources mentioned today will also be shared on that page. And please don't forget to register for the next episode. I put the link in the chat. I also put Akilesh's email address in the chat too if you have more follow-up questions. Okay. Well, thank you for joining us, and we hope to see you at the next episode.
Thank
Bye.
you all.